Okay, now we'll start. No one join it, but I want to start. Okay, so welcome in week 7 Hydraulic Engineering PMRF live TA session. I'm Om Prakash Maurya from IIT Guwahati Department of Civil Engineering. Now the week 7 is about the non-linear, the non-uniform flow and hydraulicism. So we will discuss about some basic definition related to non-uniform as well as uniform. Also some definition which is useful to study the non-uniform flow and hydraulic jump. Also we derive some formulas or concepts which is related to non-uniform flow, also uniform flow and hydraulic jump. This is a very important topic, exam point of view, also application point of view. Now moving ahead, the classification of flow. So classification of flow is very important for open channel flow, because terminology we use in open channel flow like steady, unsteady, uniform, varied, that is also varied flow is known as non-uniform. Always remember, non-uniform flow may be gradually, may be rapidly. What is the meaning of gradually and rapidly we will discuss in the later section, but for mean of time, try to understand the unsteady flow and steady flow may be uniform varied. Steady flow may be uniform and varied. Okay, so definition of steady flow let us discuss in the next slide. Here it is not given. Here I want to discuss about the steady flow. What is exactly? So steady flow is nothing but, if let us suppose I want to see a channel from top and I want to measure a velocity at a particular point at a given cross section. Let us cross section is given and I want to measure the velocity at a particular point on the top only. Okay, so steady flow is nothing but if we measure the velocity at 8 a.m. The velocity, if T1 was 8 a.m., the velocity V1 was 10 meter per second. T2 is equal to 8.5 mm, 5 am. Again, your V2 is equal to 10 meter per second. So that means change in velocity with respect to time is equal to 0. So this is the definition of a steady flow, and unsteady flow is just opposite of the steady flow. Change in velocity or any fluid flow parameters with respect to time does not equal to 0. So this is the basic definition. I think someone joined. Let me see who has joined. Okay. Oh, Partha. Hello, I am audible. Hello, Partha. Hello, I am audible. Please, if yes, please write in the chat box whether I am audible or not. Partha, I am audible. Okay, let me check. Hello, hello. Yes, I'm audible. Okay, I think Partha have some network issue. No problem. I will upload the video. Okay, let us discuss what I was discussed. Basically, the steady flow and unsteady flow. So, steady flow is nothing but the change in if fluid flow parameter. Let us, for example, the velocity. If let me put it in the full view mode, dv by dt does not equal to 0. Change in velocity is equal to 0. And here just opposite. Previously, I have discussed conceptually. Okay, so unsteady flow may be uniform and varied. That is non-uniform. Unsteady flow, uniform and varied. Steady flow may be gradually rapid. Unsteady flow may be gradually or rapid. But unsteady flow, this is the case only when unsteady flow, unsteady flow, unsteady varied flow or non-uniform flow you can say. Here also steady. This will be only you can see in the channel only when steady non-uniform flow. So this is the whole idea. Now moving ahead, very basic definition: uniform and non-uniform flow. So basically uniform and non-uniform flow is nothing but let me little bit. Increase the size. Okay. Okay, uniform and non-uniform flow. So here nothing difference, just in the steady flow we were interested to see the velocity changes at a particular point with respect to at a particular point with respect to time at a particular point p1. But in uniform and non-uniform flow what we see at a particular time we will see at the several point. Let us suppose if we want to measure this channel section of length x or delta x, you can say, in between delta x velocity at a particular time will be similar. Let us suppose at this point 2 meter per second. Here also go back. Here also 2 meter per second. Here 2 meter, 2 meter, 2 meter per second. Everywhere. Okay. So if the flow velocity at a given instant of time does not vary within a given length, that is delta x of the channel, then the flow is called uniform flow. So always remember steady and uniform flow. Similarly, just opposite of this definition, we known as the non-uniform flow or varied flow. It is very, very important. So if the flow velocity at a time varies with respect to with respect to distance, the flow is called uniform flow or varied flow. Here one, it is very, very important, you know the acceleration in case of fluid flow. If we derive this acceleration of fluid particle as per the Eulerian mechanics or Eulerian approach, you will be fine. If I want to see the acceleration in x direction, let us suppose water is flowing in this direction and I am going to assume this x direction. So what you will get, and the velocity in x direction is u. So du by dt plus u du by dx plus v du by dy plus w du by dz. So this is the expression. This is the expression of acceleration when you will derive assumption. When you will derive the assumption behind this equation, assumption is a fluid particle. Basically, Euler, we have derived this equation using the Euler approach. Okay, but here, and this term is known as local acceleration and this term is known as convective acceleration, right? So the convective acceleration in uniform flow is zero. Why it is zero? Because change in velocity with respect to distance with respect to distance is zero. If change in velocity with respect to distance zero, so acceleration in case of uniform flow is only du by dt. So here it is written similar thing. In other words, a flow is considered uniform as long as velocity in the direction of flow at a different location along the channel remains same. So this is the definition. So anyone join, I think. Let me discard. Okay, Bhuvan, I am audible or not? Okay, I think he has some network issue. No problem. Okay, so now we have done these things. Bhuvan, I am audible? Please write in the chat box yes or no, whether I am audible or not. Because I have checked by my mobile, I am audible, but I don't know from your side whether I am audible or not. Anyway, I will upload the video on YouTube. You can go in your free time, no problem. Okay, so let us put it in the full view mode. Okay, here it is very, very important whether the non-uniform flow when will be the rapid varied flow or gradually varied flow, because in open channel flow these two topic is very, very important as your exam point of view, also your competitive exam point of view. So now depending upon the rate of variation, depending upon the rate of variation with respect to distance. With respect to distance, this means in a short distance or in a long distance, how your flow parameters or depth or velocity changes. So here the flow may be classified as gradually or rapid varied flow based on what? As the name implies, the flow is called gradually varied flow if the flow depth varies at a slow rate. If slow rate with respect to distance. If let us suppose your distance is increasing in this direction, distance is increasing, but your depth is varying very slowly, not rapidly. If here was depth is this much, then your slowly your depth is going down or rise, whatever. So this is called the gradually varied flow, but this is non-uniform flow. Always remember, gradually varied flow or rapid varied flow is a non-uniform flow. If this variation in a very short span of length, then this type of flow is known as the varied flow, rapid varied flow. So here you can see, whereas the flow is okay at a slow rate distance, whereas the flow is called rapid varied flow if the flow depth varies significantly in a short distance. Let us suppose if your distance is like that, but if water is flowing like that and water is changing rapidly, so within a very short distance your depth was this much, depth was within a short distance your depth much very high. So this, hello, anybody? So this type of depth, uh, okay, so this type of changes very rapidly in the channel known as the rapid varied flow. So hope you will understand what the difference between gradually varied flow and rapid varied flow. Now moving ahead. So some terminology which is very important in the open channel flow. So channel may be natural or artificial, you know already. Artificial channel we use for irrigation purposes like canal and small channels, or also for experimental work we use the artificial channel, glass or wood or concrete or metal also. So various name have been used for artificial channels or natural channel. You know already the natural channel, generally we know river. River always natural. Okay, so artificial channels, there is the various name depending on the utilization. So what are the names? It is very important. A long channel having a mild slope. What is mild slope? We'll discuss in the gradually varied flow chapter. And here I have slides related to gradually varied flow. Later, after 1 hour, maybe we'll discuss about the all slopes. What are the possible slope in your gradually varied flow? So this is very important. Okay. So a long channel having a mild slope usually excavated in ground called canal. You know already, I think you have everyone seen about what is a canal and everything. So the channel supported above the ground. This is very. The channel supported above the ground and built of wood, metal, concrete is called flow. So this is we generally use in experimental work. Sometimes we use rectangular, sometimes flow may be sinus or meandering, sometimes maybe braided. So this type of channel we use. Okay, now what is soup? Is a channel having a bottom, very steep bottom slope and almost vertical slides. So very steep bottom. This is known as soup channel. A tunnel is a channel excavated through a hill of a mountain. Let's suppose mountain is there and in between mountain you have made the tunnel for water supply and maybe another thing also. So this is the tunnel. Okay. Now a short channel flowing partially full is referred as a culvert. Culvert is nothing but it may be the covered you might have seen in your village area road. If road is there, the for crossing the water from one side to another side, culvert generally you can see. So not full, half, partially, it may be the full up to that much or maybe up to that much. So this is the culvert. Now moving ahead on the next, a channel may be prismatic and non-prismatic. Prismatic channel is nothing but if cross section, what is, let us read the actual definition. A channel having a same cross section and bottom slope throughout is referred as a prismatic channel. Here, remember, we have addressed two things. What? A channel having same cross section and bottom slope. All the cross sectional area, not area, the cross section shape actually we are talking about, and bottom slope, and also theta. Two thing is very important for prismatic. Remember, where a channel having varying cross section or bottom, whatever, if anything, let's suppose your cross section is throughout of the channel is same, but theta is changing, increasing or decreasing. So what will happen? This type of channel we known as non-prismatic. If both are changing, always your, if anyone changing, non-prismatic channel we can tell. Note, a long channel may be comprises of several prismatic channel. If a channel is very long, maybe up to that much your cross-sectional area and theta is same. That is theta 1 and CS1. In this, between this, your theta 2 and cross-section area is same throughout the channel. So this is the actually the meaning of this line. A cross-section taken, what is the actually cross-section? Let us discuss. A cross-section taken normal to the direction of flow. This is the flow direction. If you will see in this channel, this is your flow direction. Okay. So in this is your flow direction, whether it is how many join actually. Okay, Ratna say I'm audible or not? Because no one.
Yes, sir, audible, sir.
Okay, whatever I'm writing, it is visible.
No, sir.
Oh, you are not able to see. Okay, okay. Now, now you can see.
yes, sir.
Okay, okay. Oh, after putting in full view mode, you are not able to see. Okay. Okay. So actually, what is the cross sectional? What is the cross section? It is we always choose the cross section normal to the direction of flow. So here it is written section BB. If your flow is like that, flow direction is that. So normal to the flow, we choose the cross section to the direction of flow is called the channel section. So BB here is the channel section. Sometimes here D and Y, here you can see the difference between D and Y, but sometimes D and Y we can take equal when the theta is very less. So generally, in practice, theta is very less. So we always take the D is equal to Y. Okay. So here you can see the datum and all. Okay. The flow depth here is Y. You can see the depth of flow is Y at a section. At this section, the flow depth is Y. Flow depth we take the actually the perpendicular to the not surface, not the perpendicular to the surface. Actually the perpendicular to the surface is this, that is the water surface, but we measure the flow depth as a vertical. So here it is written, the flow depth is a vertical distance of the lowest point of the channel section from the free surface, from the free surface to, that is a vertical distance, but the depth of flow D is the depth flow normal to the direction of flow. It is normal to the direction of flow. It should be normal. This is not normal. If you will, it is some at angle, but this is normal 90 degree. So this is all. And what is stage? Jet is the stage is the elevation or vertical distance of the free surface above the specified datum. If this is the datum from here to the distance up to the your free surface or the water free surface, and weighted perimeter and width, everything I have discussed earlier. So energy coefficient, you all know why we are using the energy coefficient in the derivation and everywhere, because of the we convert the things from point velocity to the average velocity. So due to the effect, due to the this assumption, we use the energy coefficient. So this is the derivation. So you please go through with this. I will not discuss much more about that. We'll focus more here on the question problem solving session. So, and momentum coefficient also very important. So here similar things. We use we use why the momentum coefficient, because let us read. The similar to the energy coefficient, a coefficient for momentum transfer through a channel section may be introduced to account the non-uniform velocity distribution, because these two things is come in the picture because of the your velocity distribution in the channel is non-uniform. This is the non-uniform velocity distribution, and uniform velocity distribution is like that. Throughout the your velocity value is same, here, but here is u1, u2, u3. So for converting from this to this, because it is very easy for your calculation and analysis, we use the alpha and beta, energy coefficient and the momentum coefficient. This is the basic fundamentals behind it, and how we derive it is very easy. If you have any doubt, you can write me mail. Okay, so typical value of alpha and beta is given here for regular channel and the natural channel, river under ice cover and the river valleys and over flooded. You can go through this table. Now moving ahead, conservation of mass. So today's topic is hydraulic jump and non-uniform flow. So conservation mass is nothing but how much water is coming and water is going. So if you will find out with the several assumptions, you will at the end of the derivation you will get Qn is equal to Q2. So or A1 is A1 V1 equal to A2 V2. So you please go through. I have discussed in the later, I think in the previous class I have discussed these things, so no need to discuss here. But conservation of momentum is very very important, and this is related to your hydraulic jump. So now I want to discuss about the conservation of momentum. So it is nothing but conservation of momentum is force is equal to your second moment of Newton's second law actually. Force is equal to nothing but rate of change of momentum. So summation of force. So how much force is acting here and how momentum is changing. But that is rate of mass inflow and rate of mass outflow. So if you will calculate rate of mass inflow at section 1, if we consider a channel, the channel and a control volume and a section 1 and section 2, so how much mass in and how much mass out from here. So if you will calculate nothing but if mass is your rate of mass flow means dm by dt. You can say for a rate of mass flow, but if you will calculate these things how you will, but m is equal to rho is equal to m by v. So m is equal to rho into VL volume rho v. Okay, and you have the extra term here t. So this is represented by m dot. If we represent these things m dot is equal to m divided by t. So what is m? Rho into area into length, and this is t. So here rho a or L by T is velocity. So rho AV. So rho AV you can write also like that. Rho area into velocity is discharge. So rho Q. So that thing here is written. This is the gamma. Gamma is equal to nothing but unit weight of water here. Rho Z. So if you will put here rho Z, it will come like GZ cancels. So rho Q. So similarly, at the time rate of change of momentum, time rate of momentum at section 1. So beta 1, why we have used here beta 1? Because of the energy coefficient. Later we neglect these things after assumption. Okay, so here for sake of your understanding, beta is here there. So your discharge rate of change of momentum is what? Mass into velocity. This is the momentum, but here asking about the time rate of momentum, so m dot into v. So this is m dot and v is v1 at section 1. So similarly m dot 2 and v2, and the time rate of increase just minus the m dot 2 minus m dot 1. You will get these things after putting the all forces is what? Force in the x direction, in this direction, and your w sine theta because of the weight one component will come the w cos theta, and w sine theta is your plus, and the pressure force is here also, here P1, and from this side is P2. So P1 is nothing but how you will calculate. This is your pressure at that point. So basically we calculate these things using the your formulas. So if you will, it will be actually at the centroid of the section, the your P1, not at the mid of the. So P1 here and P2 here, and this depth is at section 2 from the top, actually not from the bottom, from the top. In this derivation we have considered from the top, so Z2, and from the top is Z1. So basically your P1 is concentrated. We are talking about force here, not the pressure. So pressure force, that is the your pressure into area. Pressure rho g h you already know. So rho z is the gamma and h is the your depth from the top. So rho h into area. So for at P1 Z1, so here the h is equal to Z1. So Z1 here is 1. Z1 A1 and Z2 A2. So this is a very basic things, not tough here. So if you will calculate your force, so P1 is this one, and P1 in this direction, P2 just opposite, so minus, and here plus, and Fe is nothing but your the frictional force. So now force is equal to your rate of change of momentum, mv by dt. So rate of change of momentum is these things, and we have put here your, this is the force things at the gamma. We have used here already rho, and this side, you have put gamma is equal to rho z, so z cancel, so your rho b2 and q2 v2. So similar like that. Now very interesting. uh, so here b1 b2 is equal to 1. Why? If if the flow velocity is uniform at section 1 and section 2, so here we have make the assumption your flow velocity is uniform, so b1 beta 1 beta 2 is equal to 1, so it is neglected. If you will multiply one anything, it will give the same thing. So, and Fe, note that Fe is the external shearing force acting on the volume of fluid and does not depend upon the energy loss occurring inside the liquid segment. So here, what actually, now if you move, so equation 16, actually this equation, in this equation, general application of the momentum principle, and let us for the simplified case, if we assume a prismatic channel with a horizontal bottom, that is your theta is equal to 0, horizontal bottom is this, and so if theta is equal to 0, your sine theta term will be 0. And another, uh, if we assume the channel bottom and the side are smooth, if the channel bottom and side are smooth, it will be 0. So this equation with lots of assumption is uniform velocity, theta is equal to 0, and smooth bottom and wall, both bottom wall and side wall. So with this assumption your derivation is like that. So if you will rearrange these things, q1 is equal to q2, it will give these things. So how you will get, let me discuss here, q2 v2 minus q1 v1 is equal to g a1 z1 minus g a2 z2. How you will get, basically your q1 and q2 is same, q1 is equal to q2 is q. So if you will put this side, okay, so q, v2 minus, 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 q, v2 q v1 equal to g a1 z1 minus g a2 z2. So your v1 term, one side, put it just one side your v1 term. So q v1 plus g a1 z1 and q v2 plus g a2 z2. So this is the after v2 and a2, just separate out the term. Okay, and now what you will do for getting these things, this expression, so you will actually divide or multiply by the g throughout the your equation. So what you will get if you will do these things, or g a1 you can also say, if you will divide the whole equation by g a1, so what you will get, so here is the velocity, so v2 nothing but basically q v2 a2 by a2. If we do these things here also, g, or also we can, if we do these things, I will do the another line, q v1 a1 by a1 and g a1 z1. So here velocity and area, it will become the q and q square, so by a2 plus g z2 a2, similarly this side q square a2 plus g a1 z1. So here if we put multiplied by g throughout, what you will get, g by g, here also g by g. So if we take the common g and g, g and g, this if we take the common from both sides, this will be automatically gone. So a2 z2 equal to q square g a1, here a1 plus a1 z1. So this is the expression you will get after the derivation of the momentum conservation. So this expression is known as, uh, in the open channel flow, basically the specific force, and what it indicate, that is your in which Fs referred as the specific force or the momentum function, since each term of the right hand side of equation represent the force per unit weight. This term is represent the force per unit weight. This is also represent the force per unit weight. Why we call this is the specific force? Because this is the having the unit of volume. You just see the meter cube. But why we say this term is the force? Because of the it represents the force per unit weight. That is the how much force per unit of the, if we see the water flow. So per unit of the water, per unit weight. So actually how the force per unit weight. So meter cube is, if you will see one thing, gamma is equal to Newton by meter cube. So force Newton divided by your unit weight. This is unit weight. So Newton per meter cube. What it will give? Meter cube. So this thing is this force per unit force per unit weight of water. So this is represent. Always remember, very very important. Sometimes in the interview, people asking about why this term is known as the force because it's having the unit of a unit of volume. Why we tell? So the reason behind it because it represent each term represent the force per unit weight of water. So it is very very important. So now the equation of motion, or you can say the Bernoulli's equation. So this equation I have discussed in the last classes. So here no need of this equation for discussion. Okay, so here I have one question regarding the hydraulic jump. This question is very very important. The gate 1991. So what I have discussed in the previous the conservation of momentum, these things will be utilized here in this equation, in this question actually. So what we have derived using the conservation of momentum, your specific force Q by GA plus Z1 A1 equal to constant. So at section 1 and section 2, it is very very specific energy is not constant here. Why here we can also use the specific energy, but why we are not using? Because of in between the during the hydraulic jump and some energy losses, and we don't know the how much losses. So we have the only one option, what a specific force expression, that is the momentum conservation equation. At section 1 and section 2 momentum is conserved, so that's why we here use the in hydraulic jump we always use the momentum conservation equation. Here we have used two things, one the continuity equation and momentum for solving these things. Continuity equation a1 v1 a2 v2 and the your momentum conservation equation for solving the hydraulic jump problems. Not energy equation because of during the hydraulic jump some energy losses and we don't know the how much losses, so that's why we cannot apply. So please try to solve this question A, and conjugate depth is nothing but the depth or sequent depth. These before jump and after jump, whatever we get the depth in the channel known as the conjugate depth or the sequent depth. This y1 and y2 are the conjugate depth, or the you can say the sequent depth also. Alternate depth we talk in the energy where we use the energy things, specific energy at a particular fixed specific energy, we get the two depth known as the alternate depth, and another at a constant your specific force we get the two depth during the hydraulic jump known as the conjugate depth or the sequent depth. So please try to solve the question 1. The conjugate depth at a location in horizontal rectangular channel 4 meter wide or 2 meter and 1 meter. Conjugate depth are given. Conjugate depth is 2 meter and 1 meter, and the width of the channel is 4 meter. The discharge of the channel is meter cube per second. Please try to solve this question. It is very very easy. So please Partha and Vashna and Ratnasiri try to solve this question. Okay, someone asking about the clarify the seventh week assignment, second and ninth question. Okay, I have not seen the assignment actually because in live session there is no permission to solve this type of your whatever you're going the assignments. There's no permission to solve, but I can discuss the concept, no problem. But before that, please try to solve the question number one and question number one is visible. Ratnasri, you just Partha, what you can write yes in the chat box if it is visible. Otherwise, I read out for you. Is it visible? Okay, 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 thank you. Okay, thank you. So please try to solve. Very important question. This is a gate question. So let me share the not possible actually. Let me see. Okay, it is visible. Okay, you are telling the answer is 4.339. Okay, let me check. So for that, I want to take a new slide. Okay, the question is given like that. Conjugate depth at a location in a horizontal rectangular channel. Here theta is 0 horizontal because so you can use directly this equation because there is no role of theta here. 4 meter wide and 2 meter and 1 meter is the conjugate depth. Okay, so your actually y1 is given 0.2 meter and y2 is given 1 meter and width of the channel is given I think 4 meter. Yes. So discharge is asking. So you know the specific because it's the hydraulic jump things. So you will use the specific energy. So Q square divided by A1 G plus A1 Z1. Here Z1 is if rectangular channel is there. So here Z1 is equal to y2 by.
Sir, your voice is not audible, sir.
Oh, sorry. Yes, no problem. Now you will. Thank you. Okay, so here in the question is given actually y1 and y2, and that is the conjugate depth or sequent depth you can say, and the width is this. Your z1 is equal to y1 by 2 and z2 is equal to y2 by 2. And the here you will use this specific energy, because not a specific energy, not a specific force, because this is the case of hydraulic jump and you don't know the how much loss is there in the jump. So you have only one equation, that is the hydraulic jump, had no specific energy equation, and your q is equal to a2z plus a1z1, a2z1. So your Z1 is equal to 0.1 meter and Z2 is equal to 0.5 meter. And if you will put here Q not Q1, A1 is your B into A1 is how much? 4 into 0.2, that is 0.8 meter square, and A2 is equal to 4 into 1, that is 4 meter square. So 0.8 into G 9.81 plus A1 0.8 into 0.1 is equal to Q square, here also square. A2 is how much? 4 into 9.81 plus 0.8, here not 8 because A2 is 4, so 4 into 0.5 as your Z2. So if you will solve these things, you will get how much? Let me calculate. So your here is 2 minus 0.08, and here your q square, and you will 1.08 into point 9 9.81, actually not point, minus 1 by 4 into 9.81, this one. So your 2 minus, let me first calculate this fraction part, 1 by 0.8 into 9.81 minus 1 by 4 into 9.81. So it is equal to divided by 0.1019. So if you will divide, here is square, so 2 minus 0.08 divided by whatever. Now you take the under root. Yes, that is correct. Q is equal to your 4 point. You will, if you will take the square root, you will get these things, 339, or you can say 4.34. Okay, so your answer is correct. Now we move on the second question. Question number 7 is visible.
Yes, sir. Visible, sir.
Okay, please try to solve. The question 7 is actually the telling about Okay, first to solve the question 7, then I will discuss some concept. Move on question 2. In deriving the equation of hydraulic jump in the rectangular channel in term of conjugate depth and the initial fluid number, what you need actually the continuity equation and energy equation, continuity equation and momentum equation, equation of continuity or momentum and energy, all the gradually varied flow equation is used. So which option is correct for this question? So this expression is nothing but you just please reply the answer. It is just I.
B, sir. Option B, sir.
Okay, you are telling the option B. Yes, definitely continuity and the momentum equation because of the we are talking about here the hydraulic jump, and in hydraulic jump loss of energy is there, so we never use the energy equation. Okay, yes, option B is correct for this. So this expression is come when you will solve the above equation. Which one? This one. If you will arrange here your y2 and y1 is there, because if you will put the a1 b a1 formula, that is the b and a1 y1 and a2 is b and y2, so you will get the equation like this. So your y1 is equal to this expression. So this expression is the ratio of your conjugate depth. Ratio of conjugate depth is what? 1 by 2 whole bracket, that is open bracket, minus 1 root under 1 plus 8 f r2 square. You always remember. Sometimes this equation you will see y1 is equal to y2 by 2. For you remember, just I want to minus 1 here plus 1 plus 8 f r or fruit number 2 square. So you always remember in the right hand side, if y2 is above, so your fr2 will be the similar. That is the your fr, that is your fruit number corresponding to y2. Always remember. So if you will remember these things, you never forget this formula. Because sometimes during the solving this question, sometimes we may face the problem whether the fr1 and fr2, because we not have the time to solve the entire equations and derive the entire equation. So sometimes the trick always help, really help. So please try to solve the question number 2. The discharge from a spillway on a horizontal floor, here also theta is 0, is 8 meter cube per, that is cubic per meter width. Okay. If the depth before the jump is 50 centimeter, the depth after the jump is in meter what? So in the previous first question was given all two width was given, but in this question the asking about the another depth. But here the discharge is given. So you can go through this formula. Very easy. First calculate the FR and all. Okay, I will tell. So whether this one you will use or above one you will use, which one you will use, just think. After this question, we will take 5 minute break. Okay, please try to solve. I'm going for break 5 minutes. Okay, you are telling the 4.86. Okay. Let me check. So the for that I will take new slide. Okay. The question is telling the discharge of a spillway, that is the your small q is given like 8 meter cube per second per meter. Now, oh, next. And your if the depth before the jump is 50 centimeter, that is your y1 is given. 0.5 meter. The depth after the jump in meter. So here you need to calculate your y2. So y2 is y1 by 2 minus 1 plus, if here y1 you will use this 8 f1 square. So this is the whole equation. So what is f1? You know already, v1 by root gy1. And what is y? What is actually velocity? Your velocity is equal to discharge by area, always know. So b into y, and q by b is equal to your small q by y. So it is 8 divided by, we will put y1 value, y1 is 0.5, so it will be 80 by 5, so you will get 16 meter per second. So 16 divided by 9.81, and y1 is given your 0.5. So if you will calculate 16 by root under 9.81 into 0.5, 7.22. So here you just put y2 is equal to y1 is nothing but 0.5 divided by 2 minus 1 plus root under 1 plus 8 into 7.22 square. So you will get 0.5 divided by 2 into minus 1 plus root under 1 plus 8 into fr1 square, that is 7.22 square. Yes, it is equal to 4.86. Okay, your answer is correct. So now moving ahead on the next question. Actually, these content I am following, whatever I was teach the previous, these all content I am following. For these content, actually, I am following the your Hanif Chaudhary book, Open Channel Flow. So here is one example from the Hanif Chaudhary. It is very important. So a reservoir, whether I'm audible or not. I'm audible? Yes, I
Yes,
think
sir.
audible. Yes, please. The question 2.2 is visible?
Yes, sir. Visible,
Yes,
sir.
okay. Please try to solve. Let me read, because sometimes in the video not visible the questions because of the poor connectivity. So it is better to read the question. So example 2.2, the reservoir level upstream of a 30-meter wide spillway for a flow 800 meter cube per second is 200 meter. The downstream river level for this flow is at elevation 100 meter. Determine the inward level of a stealing basin having the same width as the spillway so that the hydraulic jump is formed in the basin. Assume the loss in the spillway are negligible. All losses here you need to assume the negligible. So upstream water level is 200 and downstream water level is 100 meter is given in this question. Discharge is given 800 meter cube per second and width is given 30 meter. And the question is asking about, if you will read, determine the inward level of a sailing basin having the same width as the spillway, so the hydraulic jump is formed in the basin. So here hint is given, the hydraulic jump is formed. So you go through the your basic concepts, so you will get. Okay, so now we'll discuss about the answer of this question because we have quite the time, the limited time. Now I want to discuss. So in this question, you need to calculate your actually the elevation of your sailing basin. So in this question, if you draw the figure, what you will see, a reservoir will get the Z is equal to 84.18 meter. So sailing basin inward should be 84.18 from the jump. So this is the whole answer of this problem. This is a very important problem. Now the hydraulic jump at sluice gate. This is also important. Here the concept is, so now I will discuss concept hydraulic jump at sluice gate, and then after this question, actually at sluice gate what is happening here, this line is very important, this here, assuming there is no loss at the gate, there is no loss, so E1 and E2 at the place of E1 and E2 will be the same. Your specific energy at E1 and E2 at section 1 and section 2 will be the same. This is a very important concept here. However, because of an additional external force between section 1 and 2, here your specific force will be the not equal. Because of why? Because of the additional thrust of water acting on the wall of your gate. So that's why your at the section 2 and section 1, a specific force will be not equal, but energy will be the equal. Now, so Fs1 and Fs2 will be the not equal. Therefore, there is loss of energy in hydraulic jump, of energy in hydraulic jump. So specific energy at section 2 and section 3 will not be equal. So I think you hope you got the concept. Not equal, but here there is no loss of force because of here we assume the smooth wall, there is a loss due to the shear is very negligible, so at fs2 and fs3 will be the equal. Here the conclusion is that, and one thing more, if you will see the thrust on the gate, how much thrust is acting on the gate is equal to your difference between force f1 and f2, because force is not equal because of the thrust at point 1 and point 2, section 1 and section 2 thrust specific force is not equal because of the thrust. If we differentiate these things, we can get the magnitude of the thrust. So here it is given. So conclusion point is that at section E1, at section 1, energy at E2, energy equal. But force 1 does not equal force 2. F2 equal to F3 because of we have assumed the negligible loss due to the shear, but Z1 is your E2 does not equal to E3 because of why? Because of loss in jump. Here the thrust acting on gate. So this is the whole idea. And your magnitude of the thrust, how much? Your that is rho z into force. That is the specific force. you have to multiply with rho g, because this F is represent the specific force, not the magnitude of the force. So F2 or S2 you can write here. So this is a three equation. And loss in energy, how you will calculate? You will calculate the loss in energy loss. So your E2 minus E3. So here is the four concepts. Always remember, very important. So question is what related this? A hydraulic jump is formed in a 5 meter wide outlet at short distance downstream of a control gate. This is a control gate. The short distance downstream of the control gate and 5 meter wide outlet. If the flow depth just up downstream of the gate, just downstream of the gate is 2 meter and the outlet discharge is 150 meter cube per second, determine what? The flow depth downstream of the jump, y2, that is, or y3 you can say, if we compare these things. The flow depth downstream of the jump, thrust on the gate, head loss in the jump. Assume there is no loss in the flow through gate. So here with this we can say E2 is equal to E3. So using these four concepts we can calculate these things. In the question is given like that. If you will see, the 2 meter is if the flow depth just downstream, it is given just downstream. So just downstream means y2. Y2 is given. So 2 meter. Width is given 5 meter and discharge is this. So you need to calculate what in this question? Your y3 is how much? Thrust on the gate and the head loss on the gate. So formula is E3 minus E2 or U2 minus E3, because energy at U2 is much than E3. And the thrust on the gate, rho z minus Fs 21. The force at 1 is more. Why Fs1 minus Fs2? Because due to the thrust, some and specific force is losses. So at point 2. So at point 2 your force is less compared to S1. So that's why we use the 1 minus 2. Fs1 minus Fs2. Similarly for energy. Because previously was energy much, after the hydraulic, after the jump your energy got dissipated or reduced from the previous, that is from point E2, so that's why E2 minus E3. So here Q is like that, and the simple calculation is this. So here we need the y3. So for y3 what we do? For y3 we do y3 is equal to y2 by 2 minus 1 plus 1 plus fr square. So what you will do, for calculating the fr2 you need the y2, so that's why we use the here. First of all you need this formula. For calculating the parameters in this formula, what you need to calculate, you need to calculate your fr2 and the velocity 2 like that. So your y3 is 8.63. Similarly, if let me explain very briefly your y3 is equal to y2 by 2 minus 1 plus 1 plus 8 fr, here 2 is 2, fr2 is square. So your if we draw the figure here is 2, here is y3, here is y1. So you need calculate y2. Now y2 is given in the question is 2 meter. You need y3. So what you will do? You know already the formula is y3 is equal to y2 by 2. So this formula. So for that you need to calculate fr2. fr2 is equal to v2 by root g y2. So here you need to calculate y2. y2 is discharge divided by area b into y2. So discharge is how much? Your 150. 5 width and y2 is equal to 2. You will get 15 meter per second. So from here if you will calculate fr2 will come out your 11.47. Put 11.47 here and after calculating you will get y3 is equal to 8.63 meter. Now head loss, how you will calculate head loss? Head loss is equal to E2 minus E3. So E2 is Y1, Y2 plus Q square by this and minus this. So all you data know already. Y2 know and Y3 know. So if you will calculate, you will get the head loss is this. So and thrust, how you will calculate? Thrust you will calculate like Fs1 and Fs2. So Fs1 for S1 you need to calculate y1. How you will calculate y1? If you will equate this force Fs1 equal to, if you will calculate what your specific energy, that is your E1 equal to E2, E1 is equal to U2, V1 you know, V2 you know already. So V1 is 0. Why it is 0? Because it is a big reservoir. So V1 is equal to 0. Assuming the V1 is equal to 0, you can calculate Y1. If you know the Y1, then Fs1 and Fs2 you calculated using the formula of your specific force formula. So a little bit modified, but you know already how I will modify it. Why it is y1 by? Because you know a1 into z1 and this is the rectangular thing, so z1 is equal to y1 by 2, or already a1 is equal to your y1 into b, so your b is come here, so in q, so your formula become like that. You just modify it by self yourself also. So your, and you need to calculate, this is just a specific force, difference of a specific force, but you need to calculate the thrust, that is the force. So just multiplied by the unit weight and you will get the your 4 point, that is 2434.5 kilonewton. So the gradually varied flow, we don't have time, but I have, okay, so I have just quick glance. Basically, the gradually varied flow equation is very important. This is the gradually varied flow, and we calculate this for formula using the your again the Bernoulli equation is a very important here, and the lots of how the slope is your water surface profile. Actually, it is very important for your exam point of view also and your competitive exam point of view. So we don't have time. You please go through the content I have given already uploaded in the Google Drive. So please go through that. And now I have also lots of questions for you, but due to time constraint again, we cannot solve. But rapid varied flow already discussed. Here it is very, very important one thing. The type of jump actually. The type of jump sometime in 1 marks question, you can expect this type of question. Weak jump, oscillating jump, steady jump, and strong jump. So your weak jump, if your float number in between greater than 1 and less than 2.5, this is the weak jump. Oscillating jump, your fruit number greater than 2.5 and less than 4.5, it is oscillating type of jump. Steady jump, your fruit number greater than 4.5 and less than 9, it is a steady jump. And a strong jump, if your fruit number is greater than 9, the strong jump. Energy loss, you already know how you will calculate. So if you will put this formula, let me write for derive for you. So here one figure is there. If you will see here, your the depth of your gate and your water surface profile pre-jump, one figure one represent the pre-jump very low energy loss. If such type of gate is there, energy loss is very, very less, and FR generally varies between 1.7 to 2.5. Sometimes the transition, the rough water surface, that is a rough water surface, here some roller type of things is happening, and your FR generally 2.5 to 4.5. The good jump like that, least affected by tail water. So this is like that. The FR is 4.5 to 9. So you can see the greater than 9 effective but rough. So if you're here, if you will see one thing, your depth height is little bit increasing, little bit come closer to the bed. So as your depth, your closer, as your sluice gate or gate will closer to the bottom of the channel, your FR value, if you will see here, increasing. So remember these things. Now moving ahead, the energy loss. It is very, very important. Just previously I was discussed. If you want to calculate in between two, so E1 is equal to E2, E1 minus E2. So how you will calculate this? Y1 plus V1 square by 2G plus this is minus Y2 plus V2 square by 2Z. So if you will open the bracket, y1 minus y2 in one single bracket, and here plus v1 square by 2g minus v2 square by 2g. So so v1 v2 is nothing but if the width is same. So if assume the width is similar, so what actually you will get, your discharge is equal to area velocity by velocity into area, but velocity into y into b q, and here q by b is equal to y, you will get the small q is v and y1. So if you will put like that, your v1 is equal to here 2c1. So if you will put your v1 y1 is equal to q and v2 y2, because q is q1 equal to q2 Q is constant because the your width is constant throughout the channel. So from here, if you will put the all expression, that is your, so what will be the your V1? Your V1 is equal to Q1 divided by Y1, or you can say the Q by Y1, and V2 is similar Q by Y2. So if you will put here, finally you will get the expression like that. HL is equal to Y2 minus Y1 by whole cube forward. So it is very, very important sometimes in 1 marks. So this is whole about today, and this is also important one, the pressure on spillway crest. So positive pressure, atmospheric pressure, and the sub-atmospheric pressure also is there. So always remember. So thank you for today. We'll meet again on the uh, next Tuesday. So thank you for that.